Welcome to the Explainer. So today we are totally demystifying FPGA development. If you've ever stared at a raw circuit board and just felt completely intimidated, well, we're going to change that right now. We're going to approach Verilog code just like we're snapping together digital Lego bricks. By the time we wrap up, you'll see exactly how these simple, modular little pieces all combine to build a really complex, fully functional digital stopwatch.
Okay, let's dive into this blueprint. First up, we'll meet the FPGA stopwatch itself. Then, we break it down module by module. Module 1 tames the clock. Module 2 builds the logic brain. Module 3 lights the display. And finally, we'll hit final assembly and testing.
Section 1. Meet the FPGA stopwatch.
So our end goal here is a working digital stopwatch, tracking hours, minutes, and seconds. It's going to interact with the physical world using onboard push buttons and will display everything across 4 multiplex screens, meaning they actually share control signals to save pins. Now, to make this happen, we need to ground ourselves in a specific environment. We are going to be using an FPGA, a field programmable gate array, specifically the DE10-Lite development board. Think of this thing as a totally flexible hardware canvas. We're programming it using Verilog, which is a hardware description language all managed right inside the Intel Quartus software. This exact setup gives us absolute power to dictate exactly how the physical gates on the board behave.
Moving on to Module 1, Taming the Clock.
Okay, so before we can count actual seconds, we have to build our very first digital Lego brick. We're looking under the hood at the board's internal timekeeper, and we immediately hit a major physical limitation: raw blazing speed. The DE10-Lite's internal clock pulses at a staggering 50,000 million hertz. That is 50 million cycles every single second. Blink and you just miss 10 million of them. And while that gives us unbelievable computational precision, it is just way too fast to directly drive a stopwatch meant for human eyes. So, how do we slow this hyperactive clock down for human eyes? That's the big question. We have to build what's called a clock divider module. This is going to be our ultimate mathematical solution to step that insane frequency down to a nice, human-readable pace.
Let's walk through the math story of how this actually happens. To get a perfectly human-readable 100 Hz square wave, we use a 32-bit collector. Every single clock cycle, we add a very specific number to this collector. The formula is 100 times 2 to the power of 32, all divided by our 50 million Hz clock. And that math yields roughly 8590. So, by simply adding exactly 8590 during each of those 50 million cycles, the most significant bit of our collector flips at exactly 100 Hz. It is just such an elegant mathematical trick to tame that raw hardware speed.
Now, this brings up a recurring theme for FPGA engineering, and that's the balance between structural and behavioral logic. Structural logic is literally like connecting physical hardware components. It focuses on modularity, code reuse, and hierarchical gate-level stuff. Behavioral logic, on the other hand, is a bit higher level. You focus on describing the intended behavior of the system, which gives you really clear code and allows for rapid prototyping. As we build our stopwatch, you'll see engineers constantly bouncing between both of these perspectives.
Module 2, the logic brain.
With our clock safely tamed down to 100 Hz, we arrive at our second building block. This module acts as the central controller for the entire stopwatch. This is where the actual counting of time and the handling of user inputs happens, and the whole thing is governed by a synchronous counter, meaning every action happens in perfect lockstep with our new 100 Hz clock. We have our inputs, start, stop, and reset. So the crucial point is how this running register dictates the flow of time. When start is triggered, the running register flips from a 0 to a 1 and the counter increments. When stop is hit, the register drops back to 0 and the counting halts completely. And if reset time is triggered, the whole elapsed time counter resets back to absolute 0. Simple, right?
Bringing back our structural versus behavioral motif, the logic brain is a perfect example of why this balance is just so powerful. Using structural logic here means our brain is modular. We could easily swap out this time-counting module if we wanted to upgrade or optimize it down the road without breaking the whole board. But by utilizing behavioral logic inside the module itself, our Verilog code stays incredibly readable, which makes it so much easier for an engineer to simulate and debug.
Module 3, Lighting the Display.
We have a working brain tracking the time, but right now it's just raw mathematical logic locked deep inside a chip. We need a way for this brain to actually communicate with us. Enter the binary to 7-segment encoder. Think of this as an absolutely necessary digital translator.
It takes the raw 4-bit binary numbers generated by the logic brain and turns them into control signals that drive a 7-segment visual display. Those are the actual glowing physical LEDs on the board labeled A through G that combine to form human-readable digits.
And this brilliantly illustrates exactly how that translation works. Within a truth table, if our logic brain outputs the 4-bit binary input 0000, the encoder maps that directly to the 7-bit output 100000. On the physical display, that exact pattern activates the right segments to light up the digit 0. Input is 001, it maps to the physical segments for a 1. If the input is somehow invalid, the encoder just spits out an error pattern. It's this beautiful deterministic mapping from binary logic to visual light.
Let's move to final assembly and testing and see how this builds.
Okay, we have our tamed clock, our logic brain, and our display encoder. This is the climax. This is where we snap all our digital Lego pieces together into what's called the top-level entity. In this case, our stopwatch top module. The most amazing thing about FPGAs is that they process things concurrently, meaning everything runs simultaneously. The top-level entity is the master blueprint that allows these independent modules, the clock, the brain, the display, to run at the exact same time as one cohesive system, beautifully outputting our hours, minutes, and seconds.
But hold on, before we can pop the champagne, we have a real-world validation pipeline to follow. An engineer never just writes code and hopes for the best. First, we simulate a test bench. Second, we take our validated design and compile it right in Quartus. And third, we finally configure the FPGA hardware, bringing our code out of the software and onto the actual DE10-Lite board.
That very first step is absolutely vital. A test bench is a simulated, virtual environment. We use it to verify that our module functions correctly by providing virtual stimuli. We're talking fake clock pulses, virtual button presses, the whole shebang. It acts as a virtual proving ground, saving developers a massive amount of time and preventing catastrophic logic errors before our code ever even touches the physical silicon.
Once your design passes the test bench and you configure the hardware, you've done it. You have a working, custom-built digital stopwatch. And honestly, mastering this kind of top-down structural approach leaves us with a pretty provocative thought. If you can build a precise concurrent timepiece from raw silicon just by snapping together modular logic like Lego bricks, what other incredibly complex systems are out there just waiting for you to deconstruct and master next?